Hello everyone, thank you for joining. In this presentation, we will be covering conditions of a simple linear regression model. The first condition is linearity. So the linearity condition states that the overall relationship between the explanatory variable and the outcome has an approximate linear pattern. And we can assess this using a scatter plot of y against x. And I have examples of each of these conditions as well as situations where we have deviations or violations of these conditions in the subsequent slides that we will go over along with the corresponding code. The next 5 conditions deal with the error distribution. So the constant variance condition entails verifying that the variability in the errors is constant. And this condition is also known as the equal variances or the homoscedasticity assumption. This is assessed using a residuals versus fits plot. Next, the normality condition states that the error should follow a normal distribution. While this condition can be verified using a density or a histogram plot, we prefer to use a normal quantile plot, which is also referred to as a QQ plot, to more exactly determine if the errors are normally distributed. This is because otherwise we would need a large enough sample size to be able to detect whether normality exists from a density plot, which we can also verify by assessing if a bell-shaped pattern exists in a histogram or a density plot. The next 3 conditions can be grouped together since we cannot directly verify them using graphs, but we would need to know more about how the data was collected and generated in order to assess if the independence and the random error conditions, for example, are fulfilled. I've still mentioned both of the conditions here. So the independence condition assumes that the errors should be independent from each other, while the random condition assumes that the data are generated using a random process. The zero mean condition assumes that the errors are centered at 0 or that there is a random scatter of points above and below the residual equals 0 line. The zero mean condition is a feature of the least squares regression since when estimating the intercept, the residual mean is forced or set to be 0. So that condition is in a way automatically satisfied when we are using a least squares linear regression model. So in this slide, I'm going to be providing a graphical overview of linearity and in the subsequent slides of constant variance and normality conditions. We are also going to assess cases which violate these assumptions. In addition to the graphic presentation, I have the associated code for each of the simulated conditions. So in this case, for example, I'm simulating data from a normal, just a data that satisfies the linearity condition. And I have a linear model simulated here using a sequence of values from 1 to 10, 1,000 values for x. And then I'm generating noise or random error using the normal distribution with mean of 0 and standard deviation of 2, again, of a vector of length 1,000. Then the outcome or the response variable y is generated by multiplying 4.2 times x plus 2.3 plus the noise. So it's just like your y equals mx plus b equation where the slope is 4.2 and the y-intercept is 2.3. And next I am plotting, I'm constructing the model y against x, a linear regression model, and then I'm plotting that data from that model essentially, so you can either extract the y and x variables from the model, or you can also create a separate data frame of your y and x variables and plot that data here, which is what I'm doing right here. So I'm plotting the points. The y is on the corresponding y outcome line, and the x is against the x line. And then I'm plotting both of these vectors and plotting the points, as well as also plotting a line of best fit here. So we can see that this pattern is indicative of a linear pattern. There is no curvature present that would highlight deviations from normality. So the linearity condition is assessed in this plot. So next we can assess the constant variance or the homoscedasticity or the equal variances assumption. In this slide, I have simulated data according to different conditions, and then we are plotting residuals versus fitted values plot, which can be used to assess the constant variance condition. So here the constant variance condition again states that the variability in the residual or errors, and where the residual is your observed minus predicted, is the same for different values of the fitted y-hat predictor. We can see that that condition is satisfied here since there is a random scatter of points both above and below the residual equals 0 line. And this is your same model from before, so there is no non-linearity or non-constant variance added. So this again model satisfies normality. And then I have a version of this plot here which colors the points if they're positive or negative residuals, so red or blue respectively. And then I have the analogous code for how each of these residual points are color coded and plotted here using the ggplot function as well. So again, what I'm using is I'm using the same model from before. I have the fitted values and the residual values. The fitted values are plotted on the x-axis, the residual values are plotted on the y-axis. And then I'm color coding the points. If the model fit of the residuals, if the residuals are greater than 0, I'm assigning them a value of 1 and 0 otherwise. And the points that are 1 are colored red, while the points that are blue are colored, while the points that are 0 are colored blue. So in these next 3 slides, I will cover the 3 conditions that violate the observed linearity pattern and also the constant variance pattern. So the first of these conditions shows a nonlinear deviation from normality, since the residual versus fitted plot here shows a non-normal pattern as exhibited by the curvature. And in this case, I'm adding nonlinear data to my simulation model as well, since I'm squaring the x, right? So I have a 4.2 times x squared, which essentially means that my outcome is generated as a function of x, which is squared. So it's a square distribution that we have. And we can see that based on the simulation model, our graph, our residual versus fitted plot also agrees with that simulation framework and shows a curvature pattern, which is indicative of the linearity being violated or of the constant variance condition being violated. So this is an example of a nonlinear model where the constant variance condition is again, it's not satisfied. So in this plot, we show a deviation from the constant variance condition as the points show a fanning out trend. So the fanning out trend essentially means that there is less variability for lower values of the fitted. And as we go across the x-axis with increasing values of the fitted, there is increased variability in the points. And here I'm simulating a model that deviates from the constant variance condition by adding noise, by adding a simulating noise where my standard deviation, which is again your square root of the variance, is a square root function of the x. So I'm implicitly adding noise that does not satisfy the constant variance condition, and hence I can see a fanning out pattern here plotted again for the residual versus fitted plot. Next, in this slide, both the nonlinearity and the non-constant variance condition are being violated using a simulation model that codes the standard deviation of the noise to be a function of the explanatory variable x, while y is a function of x squared. So we are intentionally infusing nonlinearity and non-constant variance in our model. So here we observe both a nonlinear pattern and a fanning out pattern of points with increasing values of the fitted x. So in this subsection, I will explore the application of the QQ plot to assess normality of the residuals. The QQ plot, which is also referred to as the normal quantile plot, is used to assess the normality condition. In this plot here, we are assessing correspondence of our residuals against the theoretical quantile values that are expected under a normal sample. So we observe a straight line for this plot only if there is correspondence between the residuals and the theoretical quantiles, which signal satisfaction of the normality condition. Alternatively, deviations in this linear trend are indicative of non-normal errors, which flag deviation from normality. Above, we have a simulated linear regression model that satisfies the normality property. So this is the same model from the initial slides. There are no deviations from normality or constant variance as modeled according to the simulation framework. We next plot the QQ plot using ggplot with the defined model, and we observe that our simulation model is verified by the quantile plot. So there is a synchronicity or correspondence between the residual and the theoretical quantiles, as we can see. So the normality condition is satisfied. So next we are plotting points that are simulated according to the model that deviates from linearity. So we are squaring the explanatory variable here, the same condition that I had shown earlier with the non-linearity. So again, we see a pattern, we see a nonlinear pattern or curvature, which is indicative of the normality condition being violated. So this data is interesting because I'm simulating it to add a right skew using a simulation framework from the beta distribution. So I have a shape 1 parameter of 1, a shape 2 parameter of 7. Everything else in the model stays as it is, and I'm simulating a right skewed pattern. So we can vary the shape parameters, which I do in the next slide, to simulate left versus right skewed. But here what we can see is our right distribution skewed shows an almost a U-shaped pattern, which is further validated by the distribution of the residuals here, which are right skewed. And we can see that both our simulation frameworks and our density plots verify the right skew of the data, which is captured by the normal quantile plot. And then I'm switching the shape 1 and shape 2 parameters to skew a left skewed distribution of the random errors, again using the beta distribution function. And the normal quantile plot now shows an upside down U, which is additionally validated by the distribution of the errors shown below using the density function, which shows a distribution which corresponds with the left skew. And lastly, I have included 2 references that were useful inspiration for this video. We have the Stat2 book and the University of Virginia Stat Lab link. Thank you everyone for listening, and I look forward to engaging with you in the next video.